everyone, I'm David Wismer, a recent graduate of the Metis Data Science Bootcamp. And today what I'd like to do is do a code review of a project that I did during the bootcamp related to linear regression. The project was on UFC fight scoring, so predicting the score of a fight given the statistics for that given fight. Things like striking statistics, grappling statistics, control time, etc. I used information from UFCstats.com for the fight statistics and also from MMAdecisions.com for the judging and media scoring information. If you want to understand more about my project, you can look at my YouTube video where I went through a PowerPoint presentation of my project. You can also look at some other resources on my GitHub for write-ups or a Medium article that I wrote about the project. And all of these resources will be posted in the description below. So what I'd like to do first is just hop into my repository for this project. And again, what you'll see here is some links to project write-ups, to my PDF of my slides. But what I want to focus on today is the actual code. And in here, what you'll see is a couple of Jupyter notebooks for data preparation and also the modeling and visualization for my project. But again, we'll be focusing today on the code. We will go through these Jupyter notebooks at the end, but first we want to get to the meat of this, which is the web scraping. Well, maybe it's not the meat of it, but it's definitely an important aspect. So what you see here is a Scrapey project, and a Scrapey is a web scraping tool that is an object-oriented programming scraper, which has a variety of modules that created when you initialize the project. The most important of which are the spiders. These are the actual classes that go through and do the majority of the work. And I've got a couple of resources that I really liked for helping me to get through this project. The first is a newcoder.io article on an introduction to web scraping using Scrapey and Postgres. For my project, I did use Scrapey and also PostgreSQL for my database data storage. And this article is great because it helps you to understand setting up your Scrapey project, using SQL Alchemy to connect to your Postgres database, how to interact with that database, how to set up and work with all of your Scrapey modules that are created through the initialization process to make the entire thing flow the way you need it to. I also want to recommend the Scrapey tutorial page from the Scrapey docs, and this is nice for filling in all the gaps that you might not be able to figure out in this tutorial. There might be something that is for your project outside of the scope of this particular tutorial, and this reference here might help you fill in the gaps. If you happen to be here because you're an MMA fan and you're scraping UFC data, this was also a great resource for me. I don't know who this contributor is or how to say his name or her name, but this UFCstats.com web crawl they created was a great jumping off point for me. It helped me to understand about web scraping even before I had even looked at these other resources. And building on my knowledge gained from looking through this repository, I was able to also build a scraper on my own for MMAdecisions.com. So I highly recommend looking at this web crawler here if you are working with UFC stats in particular. And just a quick look, UFCstats.com is the data source. I might pop into this during the code at some point. And MMAdecisions.com is where you get all the information about how the fight was scored and how the media scored the fight as well. So, jumping back into the module here, as I mentioned, the key classes are the spider classes in the Scrapey project. You've got some other things in here that will be important, things like items. The newcoder.io tutorial gets into creating items and how to use those with populating your database. I don't think you'll touch middlewares very much. Models, not very much either. Pipelines, you will have to adjust a little bit. Queries is something I created myself just to be able to query my database to get information for my actual project. Settings as well. Tools is something that you may or may not need I believe there were some things that I created myself in there just to be able to import them and keep my code a little cleaner. So jumping into the spiders, if we open up the code for the spider classes, what you'll see here is first some imports at the top, of course. Some of this stuff is specific to my project, things like the string import here. I don't know how to say this, unide code. And some of it is things that you're probably going to want. You know, I wanted to be able to close my spider. When I saw exceptions, I wanted to be able to do certain things. It'll become more clear as we go through the actual code. So I built, I believe, 3 different spiders. The first one is a performance spider. So a performance in this context is a fighter performance in a fight. So say Conor McGregor is fighting Dustin Poirier. I want to know, how did Conor McGregor do in each of the different rounds in that fight? What were his striking statistics, his grappling statistics, the control time in each of the different rounds? So what this scraper will do is it will go to the events page on UFCstats.com here. For each event, it'll click into the event and you'll see a list of fights. For each fight, it will click into that fight. And then what you see here is information for each fighter on a per round basis as well. And so what I'm really grabbing here is this significant strike information on a per round basis, and also some grappling information as well. I don't see it on here. Oh, I see it. The grappling information's on here as well. Submission attempts, reversals, control time. So these are the things that are being grabbed by that performance spider on a per round basis. So what you'll see here is a couple of different functions within the spider class. You've got an initialization function. I wanted to be able to query my Postgres database, particularly when I'm actually updating the database and not just populating it for the first time. And then the key function is this parsing function. This is something that when you create a spider class, it's generally always going to be your first function in a typical Scrapey project, as you'll see when you go through the Scrapey tutorials. And what this is doing is parsing the events page. It's finding the event links and then following those links. So first, I'm prompting the user to figure out, do you want to update new events or all events? You know, the first time you run this, obviously we're going to update for every single event in the database. But going forward, we may only want to update for events that are not yet populated in the database so that our spider doesn't have to go through every single web page within UFCstats.com. So that's all that this area is doing here. This is kind of along the same lines. Eventually, we will get an event list, a list of events that we want to actually update the stats for. So once we have this list of events, which is ultimately going to be any event that is not already in our database, assuming that's the option that we've selected in our prompt, what we're going to do is yield a response. And you'll see this a lot in Scrapey projects, this yield command here. And so what this is doing is for your response, which is going to be kind of the event page that you're working off of. You know, say you're working off of this fight night. Now for this response, this web page here, what we want to do is follow the event. Oh, I apologize. We're actually working off of the event in the event list. So this would take you to the event page. So really what we're doing here is we're on the event list. We want to, for each event, go to the event page. So that's what you're seeing here. We're actually going to the event page itself. And then we've got this callback parse event. So what this is going to do, this format here, what this is doing is saying, for each event, go ahead and perform this parse event function. So the parse event function is here. And then I'm jumping ahead a bit, but what you'll see is that for each parse event, or within the parse event function, when you come down to the bottom here, you're going to see a parse fight callback. And so what this is going to do is now go into parse fight. So you can see this is like a cascading set of functions. First, we're going to parse the event page. And when we parse the event page, ultimately what I want to do is come up with a list of events. And then for each one of those events, we're then going to go to the event page, or sorry, we're going to go to, the event page. So then when we're on the event page, we're going to get a list of the fights, and that's here. And that fight list, for each fight, we're going to parse the fight, meaning we're going to go through and get all the statistics for that individual fight. So where I left off was here. We're on the parse event page. This is the first place where we're actually going to get information that we're going to include in the database. So here you'll see some things like event name, event ID, date and location, and ultimately what we're doing is using some CSS, and at other times we'll use a different method, but to get the content from the actual web page. And I won't go through how to do all of that. There's lots of tutorials out there about how to use CSS to parse these different web pages and get the information that you need. But ultimately, I wanted to collect all this information to be stored in the database in a fight, or this will be stored in an event table. And here we see that. So here we've got our item loader. This is something that was imported from Scrapey. And then we're adding values here for each of the events that we're working off of. So for each event, we want to add the event ID, the name, the date, the city the event was in, the country, the number of fights on that fight card, and also want to add today's date, the create date, in case we need to do some updates to our database in the future. We want to know when things were updated last. And then here you'll see this yield l.load item. So that's operating off the item loader. We're loading the item to the database. Now down in the Parse Fight area, we're doing ultimately the same thing. So here we're getting information for the fight itself. I'm using the URL, the unique URL for the fight ID. This is something, I got this idea from this contributor to GitHub. And for the fighter names, you'll use some CSS to get that information. The fighter IDs will be their actual links to their fighter page, the end of their URL. Those are all unique as well and are really good unique identifiers. And some other information, who was the winner of the fight? Was it a draw or a no contest? We've got, was it a bonus? Was there a bonus awarded, like a fight of the night bonus or a knockout of the night bonus, etc.? What was the method of the finish? Was it a submission finish, a knockout finish, or did it go to decision? And then we also want to know information about when the fight ended, how long the fight lasted, how many rounds were scheduled for the fight, etc. So here we've got another item loader, and this item loader is going to load information about the fight. So again, the ID, the event ID for that fight, in case we need to do some merging back and forth with the event information, the weight class for the fight, the rounds scheduled, the method. We've got round ended, who was the referee, who were the fighters, obviously, etc. So then we're going to load that item to the database. And let's move on a little bit. None of that is particularly important. Okay. So here, what we're doing here is for each fight, we're getting into an item that I'm calling round result. And so a round result is exactly what I showed here on this page. If we go into this individual fight, we go to the per rounds, a round result would essentially be this information right here, but only one line. The round result is for one particular fighter. What did that fighter do in that round? So I guess I can highlight the bottom row. It won't let me do it. So one of these rows would be a round result. If we got both of them, we would have 2 records in the round results table. So what do we need out of the round results? We need to get the round result ID, fighter ID, opponent ID, the round ID. I also have a round table in my Postgres database. And then, of course, we have all of the information about the striking and the grappling. So total strikes landed and attempted, takedowns landed and attempted, submissions, reversals, and then we've got significant strikes to the variety of different statistics. So what you see on MMAstats.com is that we've got a significant strikes breakdown on a per round basis. And if there was a round 2 and round 3, they would be showing, but this particular fight ended in round 1, so we don't see that. But what you see is we've got head, body, leg strikes. So this is 5 of what this shows is here, like our significant strikes were 8 of 20. So he landed 5 head strikes out of 17 attempts, 3 body strikes out of 3 attempts, didn't attempt any strikes to the legs. Another breakdown of significant strikes is distance, clinch, and ground strikes. And so here you see that same breakdown, but obviously different totals than head, body, leg. So that's what all of this is doing here. The way we got all of this information was up above here where, here we got our fight stats. We used CSS to get our fight table, and then we got all of our information about the strikes here, and then we're going through and actually adding them here. It'll make more sense if you're actually building this project and you'd like to go through this on your own through my GitHub and kind of test it out bit by bit. And so that's it for that spider. So we've got all of our information for that fight. And with that information, we can do all sorts of interesting things. We can report on that information in like a Tableau style format. I built a regression model that I'll go through here in a little bit. But for now, let's pause there and move on to the fighter spider. This one is not particularly relevant to this regression project. It'll be useful for future projects where I need information about the individual fighters. But because I'm just doing round scoring, I don't actually need to know much information about the fighters. Really, all I need to know is what happened in the fights and how were the fights scored. The actual fighters themselves are not particularly important. But what you'll see is if we scroll down to where we've got our item loader, what this is first doing is finding a list of fighters in our parse function. But then in our parse fighter function, you'll see we have an item loader down here. After doing some parsing on the fighter's web page, we'll add the fighter's ID, their name, whatever nickname they might have, date of birth, some physical statistics, their record, win, losses, draws, do they hold a belt in the UFC, when was their last fight, their last weight class, gender, etc. So all of this is done in a similar way using CSS to get the details of a fighter and then parse it out how we need it. One more spider. Actually, I'll skip this one. Turns out I have 4. This is a Tapology Spider. This one is going to tapology.com. And what this website has is some information about how fans enjoyed fights. So on this website, there's actually a list of the most a fighter's favorite fights from all time. So with that information, we can look at which fighters appear most often. If we can somehow determine fighter styles for individual fighters, we might be able to see which styles appear in the most popular fights across time. Also, which style matchups appear in these favorite fights across time. But for this particular regression project, it was not relevant. The decision spider was, and that's because it has, it goes to mmadecisions.com and gets all of the information for the judge scoring and media scoring on a fight. So just like on UFCstats.com, we start at a events page. So here we've got our decisions by event, and we've obviously got it by year. So I needed to go through each of those years as well, which is something that's built into the scraper. But we start here on an event page. We only care about events that have UFC in the name. There's some others that we care about as well. For instance, if it has, it might say Ultimate Fighting Championship as well. I've got some things built into the code to find those. In any case, you follow the link to the event page. You then follow the fight link to the fight page. And then here you've got information on that fight. So what we are actually scraping with this web scraper is all of this round by round scoring. And so here you see this round was scored 10-8 by all three judges actually. And then see rounds 2 and round 3 as well. What we have down here is media scores. And you can see this shows all of the information for these fighters. I don't actually know what happens if you click on this. It takes you to a tweet. Interesting. What we don't have is round by round scoring information for the media, which is unfortunate because if we did, we could look round by round and create a really robust combined average score for the judges and the media combined. Unfortunately, what this means is that for my regression project, I was looking at total scores for the entire fight as my dependent variable, and my independent variable was therefore, or variables rather, were therefore all of the statistics for the full fight rather than on a round by round basis. But as you can see, fights are scored round by round, so there is some enhancement to be had with this model if we can somehow get this to work. Maybe just having 3 judges is sufficient enough for a regression model. I decided that I wanted to have the media scoring as well because oftentimes judges aren't very good and the media are more knowledgeable than they are. Back to the spider. So, decision spider, working off of mmadecisions.com, decisions by event. We've got, let's see. This is just printing a summary of issues that might have happened during the parsing. The meat of it begins here on the parse function. And so what we're doing is getting a list of events that we need. And what it's going to do is, just like the other scraper, only scrape the events that we don't already have, or will it scrape and update all events? Generally, we're only going to want to do the ones that we don't have so far. We'll get a list and go through them. As I mentioned, we have to parse the year page, as we saw in here. So this is like one extra step to this web scraper. The reason is because the events page here, unlike UFCstats.com, it has multiple pages. So we need to determine, okay, what is the range of dates that we need to cover, and then which of these links fall in that range of dates. And then we'll parse every link within that list of years. So we're parsing the year page. Ultimately, at the end here, we have that familiar yield function. And what this is going to do is take us to the event link. As I mentioned, that was an individual event link. So now we're going to parse the event. So we've got this function for parsing the event. And as you'll remember, just like before, in the other spider, we're going to eventually parse fights. So we've got some information that we do want to get about the events, and there's also some extra things going on here in the first place. So as I mentioned, I only want certain events in the first place. I really only care about events that are actually UFC events. So what I'm doing is looking for, here I'm querying my actual database. So I want to make sure that this fight is in my database. If this fight is, some fighter from, or some fight from Bellator, a different organization altogether, I don't want to even look into scraping this information. So what you'll see here is I'm attempting to grab the fight ID from my database. I'm querying that fight ID. This is a custom function that I've built, and I'm giving it fighter 1's last name, fighter 2's last name, the date of the fight. So I'm seeing, okay, is there a fight that matches this in my database? Can I find something where McGregor fought Poirier on whatever date that fight happened on? If it's not in there, well, I've got no fight to even populate the scoring information within my database. Or this is a fight from a completely separate organization, or perhaps there might also be some instances where the information in the MMAdecisions.com doesn't quite match with UFCstats.com. The last names are incorrect, or something along those lines, in which case it won't get caught. And that's something that would get printed out in that summary that I referenced earlier when the spider closes. In any case, all of this, I'm trying to get to an individual fight. So what I want to do from there is get to that individual fight and then go parse that fight. I'm also going to be passing in some information that will be necessary. So in the Parse Fight function, here what I want to do is get the judges' round scores and the media scores from the fight page. So notice that I am capturing the round by round scores wherever it's available, just because it may be useful to have in the future. It's getting stored in my database. I just can't actually use it right now in my regression project. And this will update the database with the scoring information. So, again, we've got some XPath stuff getting information from the web pages. This is similar to using CSS. It's a different method of parsing the web pages. And then for each decision in media decisions, we're looking at the scores and the winner of the fight. So this is looking at the scores for each media individual and who their winner was. And from there we can determine, or rather we can append that information to this particular, ultimately what we're doing is creating something to be updated in the database, this media scores variable here. I'm also going to create a mean score of the media as well as a mean score of the judges and media all together. And then I've got this function here that finally updates the media scores within our database. One other thing I want to mention is that some fights have deductions. And this is something, for instance, if there's a low blow, the referee has the discretion to take a point from a fighter. These will get marked within MMAdecisions.com, and I wanted to exclude all of those from my regression project because deductions kind of mess with the score of the fight. It's something that's not captured at all in statistics, and it completely changes how fights are scored. So I wanted to exclude all of those from my project entirely. Okay. We're going to do the same thing for the judges. We're going to update their round by round scores. We obviously need to include their names as well within the database. Here we're scraping the table and getting the judge name information and the judge's round scores, and then storing it in the database. So not a whole lot of detail here on this walkthrough on the spiders. It's very granular in nature, and all of this CSS and XPath stuff is stuff that needs to be worked out individually for whatever website you happen to be scraping. And I won't get into the other modules too much, just because if you go through the web scraping resources that I've provided for Scrapey. They're great at explaining what it is you need to do for your particular project. So what I want to do is just hop into these Jupyter notebooks. So we'll start with data preparation. Once this opens up. Okay, so obviously the first thing that we need to do is run some queries and get some information pulled into Jupyter. So I'm going to clear my data frame. I've got a little function here that just pulls all of the columns for my particular table that I'm referencing. So I wanted to get the round results. I wanted to get the fights data frame, the event dates data frame. This is actually a couple of custom functions here from this database query class in a separate module. I also want to get the round scoring information from the judges. And then, I need to manipulate my data to get it in a place that I can use for my regression project. So let's see, I had to create columns for the judge score average and the combined average. So ultimately what I wanted is a single score for a fight. What did the judges and media give to fighter 1 and fighter 2 for a given fight? So I needed to combine them all together and take their mean. So I'm doing that for both the judges in total and then also the judges combined with the media, depending on how many media members there are. And let's see, some of this is just pandas stuff that needs to happen. One thing that's critical is that I needed to create the disparity columns. So again, in my particular project, I'm looking at the disparity between fighter 1 and fighter 2. I explained this in more detail in my PowerPoint presentation. And what I'm trying to do is say, if fighter 1 had 10 significant strikes landed to the head, and fighter 2 had only 5, well, that means that fighter 1 would have a disparity of +5, and fighter 2 would have a -5. And what this ultimately means is that fighter 1 and fighter 2 in the same fight their records within the database will be mirror images of each other. It's important to understand for some things that I need to do later in the project, particularly with a train test split. Moving forward, this is just merging some columns, ultimately trying to get to a single data frame that has all the information that I need for my project with my independent variables and my dependent variable. More of the same, combining scoring into single columns. Here I want to convert rounds scheduled to float and divide all remaining columns by rounds scheduled. And so the reason that I'm doing this is because some fights have 3 rounds and some fights have 5 rounds. So if you look at the scores for a 3-round fight and a 5-round fight, a 3-round fight might be 30 to 27, whereas a 5-round fight might be 50 to 45 if one fighter won every single round in that fight. And in order to make them comparable, we need to take the statistics and divide by the number of rounds in the fight. And that's true for every statistic, for strikes, for grappling information, for control time. We want to look at it on a per round basis so that we can compare all types of fights of 3 rounds and 5 rounds, and have a more robust data set. Okay, moving forward, needed to explore collinearity. So we want to get rid of some of these features, right? We have so many features. Here we see a heat map with a lot of features that are clearly highly correlated. For instance, here you see significant strikes landed and significant head strikes landed are highly correlated, makes a lot of sense. Let's see here, total strikes attempted, total strikes landed. What else do we got? Takedowns landed and control time disparity are highly correlated. Okay, so what are we going to do with this information? It's not very actionable, right? We need to think about how are we going to actually reduce these features. And the way to do that with a regression problem like this is with variance inflation factor. And so variance inflation factor is a way to look at how different how different features within your data set are correlated and how much those are impacting the actual regression model. And so when you come back with really high numbers, what that means is that they're highly correlated with another feature in your model, and it may be that it's not actually providing much benefit to your regression model in the first place. So here we see things like infinity. That's no good. I mean, even this 7 is a little high. Generally 5.0 is an accepted benchmark for variance inflation factor. So when I see these kinds of things, what I want to do is think about, okay, which of these does it make sense to consider dropping? You know, any of these with really high numbers, you don't want to necessarily drop all of them because they're correlated with each other. But I want to go through and think, okay, well, you know, intuitively some of these don't make sense to have in here. So what I'll do is drop some of these, like significant body landed here, significant leg landed, distance landed, clinch landed. These are all different types of significant strikes. And of course, they're going to be very highly coordinated with just total significant strikes, which is obviously a more important metric for judges. I didn't want to get rid of head strikes because head strikes are particularly damaging. They often land to knockdowns and things like that. So I wanted to leave that in there. So I got rid of body strikes, leg strikes, distance strikes, clinch strikes, etc. And after I did that, I reran variance inflation factor. And here what you see is a much cleaner output. You know, we've got significant strike land disparity is a bit high, which makes sense because we also have significant head landed disparity. A lot of people are going for the head. But these numbers are a lot more reasonable, and so I moved forward with only certain features here. So I also wanted to look into, this is just exploratory data analysis. Let's look at the pairwise plots. You know, some things you might be looking for here are some interesting relationships, maybe some parabolic relationships or anything that's really not just linear in nature, and you don't really see a whole lot there. The pairwise plots, the heat maps, they help you to kind of identify, okay, here's some really highly correlated variables, but ultimately I feel like the variance inflation factor is a cleaner method to actually make a decision on what to drop. I don't see anything in here particularly that gives me pause. You see some highly correlated things, but of course, actually, this is with my smaller set of variables. So if I saw anything super glaring, like a nice, perfect straight line, maybe I would consider dropping more things, but ultimately I move forward. I want to have too few features. Here I'm just describing the data set. You know, I want to make sure that everything makes sense in here. For instance, if you look here, the mean is 0 for everything except for the combined average. And the reason that all of these disparity features are 0 is like I described before. So fighter 1 has 10 strikes, fighter 2 has 5. That means the disparity for fighters 1 and 2 will be 5 and -5. So when you combine the entire database, the records should add up to 0, and they should have an average of 0 as well. So that makes sense. So here we're just kind of looking to make sure that everything makes sense. There's nothing else that I really want to call out here. And then ultimately I pickled my data to be used in the other notebook where I'm doing my my visualization and my modeling. So moving on to that notebook. What we see here first is a lot of imports, bunch of stuff from scikit-learn. You're going to see that I'm doing a number of different models, including lasso, ridge. I also need cross-validation for those. Stochastic gradient descent, random forest regressor. I've got train test split, some pre-processing things coming in as well, and then also needed to import some modules here for calculating the performance, R2, mean squared error. I've also got some visualization stuff, some stats stuff, and yeah, let's go ahead and walk through it. Again, gonna need to query some information, and then train test split. What we've got here is, I actually don't have the train test split right here. Okay, it's just down in the baseline regression model. One thing I wanted to mention in the train test split is that I'm not actually using train test split as I imported it up here. Considered using it. I think I ended up not doing that. The reason I ended up not doing it is I wanted to use a time-based split to make sure that fighter 1 and fighter 2 from the same fight either both end up in training or both end up in testing. I didn't want to do a random split of my records because fighter 1 and fighter 2 are two separate records, and that could mean that fighter 1 ends up in training, fighter 2 ends up in testing, and they're technically mirror images of each other, so it doesn't make sense to do so. So I did use a time-based split. All right, baseline regression model. So the very first thing I wanted to do is just get a model built, see what this model returns, and then we can kind of enhance from there. So let's see what we were doing. We're first getting our data from the pickle. Looks like we're doing a little bit of just kind of data cleaning here, getting some identifiers in place, merging some dates and using those dates ultimately for the split. So here we've got our training cutoff at a certain date, validation cutoff at a certain date, such that we've got, you know, kind of 60-20-20 split in terms of train, validation, and test. Here's where we actually do that split. And then we want to split the data to training and testing data and instantiate our model. So here we're going to instantiate the linear regression model. We're then going to fit the model with the X-train and the Y-train data. So back here, what we were doing is splitting our information by column. So our test data is just going to be the combined average score, whereas the train data is going to be kind of everything except that scoring information. Again, we're going to instantiate and fit our model. And once we fit our model, we can determine our intercept and our coefficients. So for each coefficient in these columns, we're going to print it out, just take a look at it. And then we're also going to print out the score of our model. So here's where we're going to use the dot score. We're going to score it on our testing information. So what we see here is we've got an intercept of 9.487. These are all of our coefficients for our features, and our scores, R squared of 0.6778, 0.2096. So this is what we're going to try to be improving upon. I mean, this as well, but I'm going to focus on R squared generally. I looked into polynomial features. This is what I mentioned before when I was saying, is there any sort of quadratic or any other polynomial relationship within our pairwise plots? There really weren't. So there was no reason to necessarily do this other than just seeing, okay, what can we find? This is a trade-off, right? Because if you're adding polynomial features, it's adding complexity to your model that you then may not be able to really explain, but it might also improve the performance of your model. It might increase your R squared. So here we can see, I did some fit transform with our polynomial features with a degree of 2 and scored the model. We did increase our R squared a little bit to 0.6904 up from 0.677. You just have to determine, is that increase worth it? I didn't think it was. And then when I increase polynomial degree to 3, I can get the R squared all the way up to 0.693. Again, not particularly worth adding all of these additional features that you then have to have in your model for such a small impact. Okay, moving on, I wanted to do a cross-validation on all of the different models that I want to test. So what do I want to test? I want to look at linear regression, lasso, ridge regression, stochastic gradient descent regression, and random forest regression. And so we need to do a couple of things to make this work. Here I redo the train test split. Here I'm normalizing data. Here I'm standardizing data using min-max scalar and standard scalar. And you need to fit, transform, and transform your training and testing data sets in order to make this work. And I wanted to see for all combinations of the different models and data types with normalized and standardized data and also just unaltered data, what happens? What creates the best R squared and root mean squared error? So moving on here, obviously I did some parameter tuning on the lasso and ridge regression and came out with the best possible that I could, and did cross validation. And here what I'm doing is really ultimately I don't think this was ultimately used actually. I intended to, but ultimately what I wanted to do was instead run a function to populate a table and print out that table all at once. So what I did here was for each of these different models, regression model, simple regression, lasso regression, ridge regression, stochastic gradient descent, which by the way did not make sense to do with unaltered data. You need to standardize your data or normalize your data first. And random forest. For each of these different types, I wanted to do unaltered, normalized, and standardized data. So I wrote a little function, and this function populates the cross-validation dictionary to be passed to a summary data frame. So ultimately, all of this gets passed into a data frame, and when I print that out, here's what you get. So here we can see all of the mean R squareds from the cross validation with 5 folds for each of the different combinations of model and data type, as well as the standard deviation, the root mean squared error, and the standard deviation on the root mean squared error as well. And you can see these are all very tightly grouped. Random forest does seem to have the best of the models. With normalized data, it appears to have the best possible R squared mean. I also performed simple validation. I won't go through this. This is without doing a cross-fold validation, just simply using all of your training data and then testing on all of your validation data a single time. I won't go through all of this, very similar code. But ultimately, we get a table down here where we've got our models, our data type, unaltered, normalized, or standardized, and then all of the information about the validation. So we've got our simple validation and cross-validation information in here. For simple validation, again, we do see that random forest comes out on top, but is it worth it? Our simple linear regression model is only behind by, looks like a single %. We have to determine, is that worth it to us? Do we care about that additional percentage, or do we prefer the ability to explain our model a little more easily with linear regression, simple model on its own? So same thing here for root mean squared error. Here, what we're doing here is simple validation for prediction accuracy. In this case, rather than using the R squared, which is looking at the predicted score for a fighter versus their actual per round score as determined by the judges and media, in this case, we're looking at our predicted winner and the winner of the fight as determined by the judges and media. And we should see a better performance here because we're just trying to pick the winner, whereas picking the actual score is a little more difficult. It's a little easier to interpret as well. So I won't go through all this code. Again, all it's doing is it's taking our actual prediction for individual fights and comparing them to the winner of the fight as determined by the judges and the media. And ultimately what we see here is we've got a winner prediction accuracy of around 85% for linear regression. It does not really improve much for any of the other models. Stochastic gradient descent comes in at 86.41%, but every time you run stochastic gradient descent, it will return a different result. Sometimes it'll be a bit lower, sometimes a bit higher. This is kind of around the average. In this case, it was interesting to see that random forest was actually a bit lower than 85%, which is another reason to consider going with linear regression. Really what I care about in this model is, does it pick the correct winner of the fight? So here we're going to do testing. Now we're going to introduce our testing data that we've been holding out this entire time, not using it for validation, obviously. And what we want to do is look at the top models as determined during the validation stage and see which of these models are working best on our testing data, which generalize best to the testing data. And so here we've got a model comparison of linear regression, stochastic gradient descent regression, and random forest regression. In terms of the R squared, they are very close, but random forest does come out on top. For root mean squared error, linear regression with normalized data comes out on top. And for winner accuracy, stochastic gradient descent comes out on top. So we've got a different winner for all three. Ultimately, we see these are very tightly grouped together. And because of that, I decided to go with linear regression with normalized data for my final model to be used for all of my visualization and a model that I would use for predicting winners in the future. The reason for this is that it's easily interpretable. I can explain through the coefficients of the different features what is important to a fight, whereas the others, when you introduce stochastic gradient descent or random forest, it becomes a bit more of a black box and a bit harder to understand, and the performance benefit is negligible, so simplicity wins out here for me. So here are those coefficients as well as the intercept, and I go through this in my PowerPoint presentation as well, but what's interesting here is that these features, as they are ordered, very much reflect the actual judging criteria as it should be done. So judging criteria for a fight is prescribed by the UFC. This is supposed to be judged first by effective grappling and striking. That's the first criterion. So whichever fighter has the better effective striking and grappling in the round should win that round. And what we see here is that our most important features are significant strikes landed and takedowns landed, which are obviously very representative of effective striking and effective grappling. Uh-oh, looks like my video's not working. I want to fix that. Give me just a second here. And I'm back. So after effective striking and grappling, you've got effective aggression, and that is, which fighter is attempting to end the fight more, which fighter is being less conservative, kind of pushing the pace. And so that can be represented by, for instance, knockdown disparity. Pardon me. Potentially control time disparity as well. So a knockdown is when you hit your opponent and they fall to the ground. That can be kind of interpreted as aggression. And in the absence of a clear winner in effective striking and grappling and aggression, the third criterion is control of the fight area, which is obviously represented by control time disparity. Potentially takedown attempt, not really. Takedowns landed for sure. When a fighter takes somebody down, they're generally in control. So these top features are representative of the key scoring criteria as prescribed by the UFC. Another interesting thing is that takedown attempted disparity is the only feature with a negative coefficient. And what this means is that when you attempt to take your opponent down, in the eyes of the judges, you are penalized. But when you succeed in taking your opponent down, you get a larger reward than you did for attempting to take down your opponent. So if you attempt to take down your opponent and you succeed, well, then you get a net positive. If you attempt to take down your opponent and you do not succeed, it's viewed as a negative, which makes a lot of sense. All right, moving on to some visualization. These are things that were included in my PowerPoint presentation. Here we're just looking at residuals, making sure that these appear reasonable. I won't get into all this, but they do appear mostly reasonable. Being along this line is a good thing. Here we've got our feature coefficients just visualized again. And again, here we see that takedown attempted is negative, and the most important features here at the top. Here we've got our predicted versus actual per round score. And what this is showing is incorrect versus correct fights. Maybe I'll actually go through some of the code on this one. So what we're doing here is first, we're using some data frame called winner prediction, regression, normalized data. This is something that was created up above. We're creating a column for, was this a correct prediction or not? And where this correct prediction equals 0, obviously that will be incorrect, and where it's a 1, we have it correct. So we're just labeling this as correct versus incorrect to then be used within our visualization here. This correct column must have been created up above when we were doing our calculations on prediction accuracy. So here we were using matplotlib to create a feature, and we're going to title it predicted versus actual per round score, do some formatting here as well. And then we're going to add a seaborn scatter plot where we're going to, on the x-axis, have our combined average. This is going to be the actual per round score as determined by the judges and the media. And then on the y-axis, we have our model's prediction. And so we then have our kind of scatter plot. What would be perfect is if we had like a nice straight line, right? It's just perfect. We just nailed it. But we have a nice upward trend, which makes sense. And then let's see. I also am plotting a couple of lines right here at 9.5, and I'll talk about why that is. So for every round, generally speaking, you have a fighter scoring 10 points and a fighter scoring 9 points. And so that means on a per round basis, the average score for a round is 9.5 points. And what that means is that if you score above 9.5 points, generally you're going to be the winner of that round. And if you score below 9.5 points, you're going to be the loser of that round. So as you can see here, the black dots, or the incorrect predictions, are centered in these lower right and upper left quadrants. And that's because the model gets it right when the actual per round score and the predicted per round score are on the same side of 9.5. This means that if our model gave a fighter 9.75 points, but the judges only gave that fighter, 9 points per round, well, okay, then we probably got it wrong. But if we agree and 9.75 is also what the model and the judges both give that fighter, well then okay, we probably got it right, because on average that fighter won those rounds. And so we see these black dots focused here. And there's a couple of cases where that's not true, but it's the general rule. Let me see, did I have anything else to talk about in this? Oh yeah, I've got some labeling and stuff here, but you can easily look up these kinds of things. They're not hard to do. Then we've got some box plots. And these box plots, again, we're doing a seaborn box plot within a matplotlib figure. got some similar formatting going on. And what these box plots are showing is, again, the correct versus incorrect predictions. And we see that the red or correct have a wider distribution than the black or the incorrect predictions. And that's because the incorrect predictions have closer distributions of features because they are closer fights, meaning that our model gets it wrong when the stats are closer together. And that means that stats weren't enough to determine the winner of a fight. Maybe one fighter, maybe the two fighters had very close statistics. Maybe one fighter even had more strikes, better grappling, but this fighter who had less strikes, maybe less submission attempts, less things that generally improve the chances that a fighter won the fight, maybe they also landed the more damaging strikes. Maybe they were really close to getting a submission attempt finished. These are things that don't show up in the statistics for a fight, and so they're the things that our model misses and will always miss. It's difficult to capture that kind of thing, but it's nice to know that when our model gets it wrong, the stats are closer together and it's not as clear who the winner is. So give ourselves a little grace there. Here's the same thing, just in a violin plot. And one fun thing that I did that you might consider doing for multivariate linear regression, it's difficult to come up with much to show kind of correlation in a visualization. And the reason is, you can easily show correlation with two variables, with an x and a y axis, and just a scatter plot that shows kind of how are things correlated. For instance, our actual versus per round score, we could easily draw a correlation line in here. And also, if you have, you can have 3D graphs with a third axis as well, but they're difficult to really tell what's going on. For instance, here, we've got 3D axis and a plane, but unless you've got the perfect angle, it's kind of difficult to tell correlation. And even then, if you looked at it from a new angle, it might look kind of different. So what this code does here is it builds a 3D rotation GIF. Or really what it does is it builds a bunch of pictures that can be then put into a website to create a GIF. And so what you'll see here is, well, not here. Here, this is just building a single visualization. But to create the actual GIF, you go through an A range of 0 to 360. That's 360 degrees. And pick your elevation. You're gonna set your kind of like skew here, and then I'll save a figure for each one of these, so that I have a picture at every single degree of rotation, and then you can put them all together to create a seamless GIF, and that does a bit of a better job of showing that that correlation. But it's just for fun. And then there's not much else to show down here. This here shows winner prediction using random forest. You can see it's quite a bit more odd, isn't it? It doesn't really have that nice correlation. Can't really say why I didn't dig too deeply into random forest. And that more or less covers what I wanted to cover today in the code review. If you have any other questions, you can certainly reach out or put some comments in the YouTube video. I recommend going to my full write-up here. Certainly this will have more information about the project in kind of a cleaner format that you can easily reference if you're building a project similar to this. I also recommend looking at my article on Medium, for which I will post a link below. Similar information to what you see here as well. So thanks for your time today. Again, if you have any questions, feel free to reach out.